So, well, before we get started, I want to just let you guys know I was very, very pleased with your quiz ones. Went through, and I think pretty much everybody got an A on that. And I want, in reading your comments, I was very pleased that some people. I have one guy that said he installed lights on the car and he used relays, and he had a better understanding now of what he was actually doing, like kind of looking back. And I had a couple students say that the assignment, the video, it cleared up some things for some people. So I always like it when there's some kind of concept or some kind of theory that we talk about in class, and you can apply it to some kind of practical situation, especially something that you're either working on or that you've already worked on. And trust me, a lot of this stuff will come up again when you guys do your senior project, your senior design project. You guys are mechanicals, so you're really electromechanicals, because I don't think anything strictly is mechanical anymore. It's always some kind of, or usually some kind of electrical system connected to mechanical system. So, but I was very pleased. You guys did really well. If you turned in your quiz early, I think I graded most of those. I think most of everyone's got graded. If you turned it in late, I might have missed one or two, as well as the homework. If you turned in homework 1, I graded that. If you turn it in, I don't know, a couple hours before it was due, it's still floating out there waiting to be graded. But I think for the most part, everybody did a good job. So thank you for that. Now, in the last class, towards the end, I had to kind of go quickly. So I want to make sure we get through this practice problem, because your next quiz, the quiz at the end of this week, will be over the information from that objectives, that week 1 objective sheet, and there'll be something similar to what you're looking at now at the screen. So we talked about this problem. I ran out of time. I want you to go through here and just take a look at this and see what you can do with it, and then we'll discuss it in detail. And this is still week 1 stuff. And once we get done with this, we'll move into unit 2. So this problem, determine the total time required to transfer 8 bits containing a serial waveform. So in the last class, we talked about data transfer. So we understand that if I want to represent a binary number, a 1 or a 0, if I want to represent a number as a voltage level, I can use any 2 voltage levels, and it's standard to use 5 volts to represent a 1 and 0 volts to represent a 0, ideally. So representing binary or machine language as voltage levels is quite easy to do. So I can hold those bits. I can just store voltage levels in the capacitor. I can put them in something called a register. Holding the voltage is no problem at all. But what if you want to move those bits around? What if I want to move bits from, let's say, the memory of a device to the microprocessor, or from your PC to a printer, or from your cell phone to another cell phone? You're moving bits around. So how do you do that? We introduced the concept of a digital pulse. There's a positive going pulse you can have and a negative going pulse. We looked at that. If you didn't see that, if you weren't here for the last class, make sure you view that on your past video link. But once you understand how to build a pulse, a positive or negative going pulse, we use pulses together to move data around, to transfer data from one place to another. Now, there's 2 basic ways of transferring data. I can do it serially, which means I can do it bit by bit. I send a bit down the line one at a time, kind of a single file. Or I can do it in parallel, where for every bit I have a wire dedicated for that bit. So if I have 8 wires, I can move 8 bits all at once. That's called parallel data transfer. And we talked briefly about the advantage and disadvantage of both. Serial data transfer is slow, but it's very inexpensive, and the system to control it is simple. Parallel data transfer it's a lot faster, but the circuitry is more complicated. So like anything, there's a trade-off. So what this problem does on the screen, you're given a waveform. Now, the top waveform is called the clock. Every digital device, your cell phone, anything that contains a microprocessor, your microwave, your PC, all of these digital devices has a special circuit called the clock. It is literally the heart of the device. It's the heart of the device. Things happen as the clock ticks. Now, somebody asked me at the end of the last class, what do you mean by a tick of a clock? Well, we refer to that as the bit time, or the period of the clock. So I mentioned periodic waveforms in the last class. You probably studied this in your math class or physics. If you have a periodic waveform, that means it has a frequency, and if it has a frequency, it has a period. So if it has a frequency, you have so many cycles or so many events per unit of time. The period would be the time for one event. And so I gave an equation that relates frequency to period and period to frequency. So this problem kind of speaks to that. And again, part A, I want you to just take out a sheet of paper and let's kind of work through this and think about how we would solve the problem. And then if you have any questions, you can ask me now about this or anything we talked about from week 1. So first question, question A, determine the total time required to transfer 8 bits contained in the serial waveform A. So we're talking about serial data transfer, and indicate the sequence of bits. It says the leftmost bit is the first to be transferred. And when they say the first to be transferred, they mean the first to be transferred in time, T-I-M-E. They give you the frequency of the clock, and then they want you to figure out the bits that are transferred, how long it will take to transfer the bits. So that's part A, and then part B, they ask a different question. So right now, let's focus on part A. So to approach this problem, if you remember, the first thing you got to do is figure out the bit time, and the bit time is always given by the period of the clock. So they gave us the frequency of the clock right here. Here's the frequency. So the first thing you got to do to solve the problem is from the frequency determine the period. And remember, the period is equal to the bit time. The bit time is the time for one bit. So you would take the frequency, use that frequency to find the bit time, and then at the bottom, the waveform A is the actual data. This is the clock, and this is the data that we're moving in the digital system. So step 1, figure out the bit time by determining the period. Step 2, use waveform A to determine the bits that you're sending. If I have a positive going pulse, then I'm sending a 1. If I have a negative going pulse, then I'm transferring a 0. And then they want to know how long will it take to transfer all 8 bits. So I'll give you a few minutes. Go ahead and see what you can do with that, and then we'll talk about it. Thank you. I was asking if anybody came up with the period.
Is the frequency in hertz or kilohertz?
Oh, it's kilohertz, thank you. Well, that would be terrible if it was in hertz. We wouldn't move any data anywhere. It'd take all year. It was 100 kilohertz, is that right? So then what would my period, what kind of period am I looking at? Period is 1 over frequency. So I have 1 over, that's many hertz. So if I do the math, 0.01, it'll come up as, it'll give me 10 times 10 to the 6 if I move my decimal around, and that's in seconds. So if you do the math here, it looks like our period is 10 microseconds. By the way, a hertz, a cycle, the unit, so a hertz is equal to an inverse second, so it's equal to an S over 1. So the units actually do work out to seconds. But if you do the math here, our period is 10 microseconds. So when I talk about the click of a clock, that's what I'm referring to. So here's a partial representation of what they gave us in the problem. They gave us the clock waveform, and then this is our data. By the way, this is called a timing diagram. This is a timing diagram. And this would be the first click of the clock right here. So this 10 microseconds, we're saying that the bit time from the transfer of this bit is 10 microseconds. And since this is a positive pulse, what this clock does is it breaks the data signal up, and I can see how many ones I'm actually sending. So I have this click, this click, this click, and for click A, that's a 1. That's the first bit to be sent in time. And then this is B, that's a 1. And then we think like that. So I'll be quiet. I want you to finish the problem. I'll give you a couple more minutes, and then we'll talk about it. About 30 more seconds, and then we'll talk about this, and then we'll move on to something else. 30 seconds. All right, determine the total time required to transfer 8 bits contained in the serial waveform A of figure 114. They want to know the sequence of bits. They're telling us the leftmost bit is the first to be transferred, and they give us the frequency of the clock, which is 100 kilohertz. So a clock is always our reference. So I actually just kind of worked this out to be easier to show you on your screen. So first we figure out the frequency, or given the frequency of the clock, we figure out the period. And remember, the period is always equal to your bit time. So that means that for each one of these bits sent, this is how long it's going to take. If we send it bit by bit, it takes 10 microseconds to send each bit. So notice here I went in and I like to, with letters of the alphabet, I'll mark each tick of the clock, each bit time. So the bit time A through H, bit time A, this is the first bit. Bit A is the first bit to be sent. We send the 1 first, and then we send the 1, and then we send a 0, and then we send the 1, then a 0, F is a 1, and then G and H are 2 zeros. So I drew it like this because sometimes that when you think about these bits actually moving, sometimes you think about this bit right here. Wait a minute. This bit right here. It's just kind of natural to think about the bits as kind of flowing this way. But actually we made which is the first to move in time. And if you think about an axis, if I put this on the XY axis, and this is my T axis right here, then the first one, T0, is like right here. That's my first bit to be sent in time. So we always think about it that way, the first in time to move in a digital system. So again, remember for the quiz, and I'm not teaching to the quiz, I just want you to remember the steps here. Given this graph, I either have to give you the period directly or given the frequency. You take that frequency and you determine the period, but the period is equal to the bit time. So now once you get the bit time, if I have serial data transfer, which is what this is, it's going to take 10 microseconds to send each bit. And since there's a total of 8 bits, down here the total time of transfer, which is what the question asked, is going to be 8 bits times 10 microseconds per bit. It's going to take 80 milliseconds, or 80 microseconds, I'm sorry. It's going to take 80 microseconds to send that data in waveform A. And notice how I drew this is the actual order in which the bits are transferred. So again, don't think of it as this bit right here moving to the right. Think of it moving in time, and moving in time. This is the first click of the clock right there, A. And so you will see that 1 associated with click A. This is your eyeball. You will see the 1, then you will see the 1, then you will see the 0 from that click. And when you get to the 8th click of the clock, the 8th bit time, we're at H, you will see the 0, and then that will be all the bits contained in waveform A. So that's if we transfer the bits in serial. It'll take 80 microseconds. But then the next part of the question says, B, okay, what if we transfer them in parallel? If it was parallel data transfer. When parallel data transfer, all the bits move at one time. So basically you have 8 lines. You have a line for each one of these bits. 1 line for each bit. And when the clock clicks, 1 bit time, each bit individually can all as a group move through those 8 lines together. And so to transfer those bits, if I have parallel data transfer, it only takes 10 microseconds, much faster than serial. And so typically with digital devices, when we're inside a digital device, we're working around the microprocessor, like memory or the actual microprocessor itself, that data needs to move around extremely fast. So inside of your device, typically things move around in parallel. Outside of the device, depending on what it is, like we're talking about a printer it doesn't have to be extremely fast. You can send those bits in serial. Now, even if it's in serial, think about it. We said 80 microseconds for the total time in serial. Well, 80 microseconds is pretty damn fast. I'm sure you realize that. But when we think about computers and digital devices, then maybe that's not so fast. But just so you have a mental picture of this, let's go back to the other diagram I showed you last class. So in the old days, your PC had a serial port. It was called a serial port for a reason. There was one line that connected from your PC to your printer, and that one line will send the bits bit by bit in serial. And so that was the first problem on the example we just did. Whatever the bit time is for each bit, you multiply that by the number of bits that you're transferring from the PC to the printer, and that will be the total time to transfer all of the data from the PC to the printer. It's slow, but it has no reason to be fast because this has its own memory in it. It'll just load up those bits, and then it'll start to print the letter or whatever it is you're typing. So talking from the PC to the printer, in the old days, now USB now is a little different, but in the old days they had a serial line. They would actually send it bit by bit. Inside of the machine though, where here I have the microprocessor, here I have memory, and these lines on here actually represent wires. This is called the data bus, by the way. This is called the data bus. If I have an 8-bit data bus, that means I can send 8 bits at one time, all in parallel. It only takes one click of the clock. Whereas here, I have to send them all down one wire. They have to go one at a time. Here, all 8 can go because it has its own wire to travel from the microprocessor over to the memory or vice versa. So parallel data transfer is much, much faster. But as you can see from the picture, this is a lot more complicated. Now, we're not showing everything here because you have to have circuits to control this. So it's a lot harder to control this system than it is the serial system above it. So like everything, there's a trade-off. Right, so anybody have any questions over data transfer, serial parallel data transfer? Matter of fact, let's just do this. Let's go to, this is the objective sheet for week 1. Let's look at this. If you understand everything on here, then you're gonna blow quiz 2 out of the water. You won't have any issue with it. So let's just kind of run through this quickly, and then we'll still have about 30 minutes for today's material. Hold on a second, let me walk, because I know there's a motion detector in here, and it's on the timer. So I'm just gonna step out here and let it pick me up. That way the lights won't go off in the middle of my discussion. All right, so just going through this quickly, the main differences between a PC and a PLC, we actually see more of that today. A PC, that stands for personal computer. A PLC is a programmable logic controller. They're both the same thing. They're exactly the same. Well, not exactly the same, because a PLC, all it is, think of it as a PC on steroids. It's a PC designed to work in an industrial environment. And what I mean by that is it's got to withstand a lot of use. It's got to withstand temperature extremes. It's got electromagnetic noise. So when I say heavy duty, I mean they're designed to, for anything for all of the extremes that you might have this thing in a freezer, you might have it out in the Sahara Desert. It's got to be able to function in extreme environments. But basically, they're the same machine. They're the same machine. We talked about analog and digital. We have to understand those two because many of the quantities, if not most of the quantities we'll measure to go inside of our PLC, those are going to be analog, but digital devices only understand digital, ones and zeros, machine language, binary. And so we understand analog to mean continuous, digital to mean discrete, but when you digitize an analog signal, remember that's a process. We have to go through and sample the points and assign each point a binary code. We got to store that code. So that's a process. If you need to review that, go back and look at the video recording on that lecture. The difference between analog and digital quantities, I'm sure you can come up with some differences between analog and digital quantities. You want to make sure that you remember when you're thinking about that, the digital advantage, and that's a big one. The digital advantage is two parts of it that we talked about at least, is that one, digital information can be copied over and over and over again. It does not degrade, and it can also be compressed. And so we call that the digital advantage. Give examples of how digital and analog quantities are used in electronics. Well, one example would be what I said already. Maybe you're watching me now on video. That's an analog capturing of data. But the fact that you're looking at your computer or your cell phone or however you're watching this, that means there's going to be some analog to digital and digital to analog conversions going on. So you can think of examples that fit what we've been talking about. Define the term binary and define the term bit. Binary is actually a number system based on 2 digits, zeros and ones. And we'll get more into that next week. A bit it's just short for binary digit. A bit is either a 0 or a 1. And we spend a whole lot of time talking about binary. Name the bits in the binary system. I already named the bits. One is called a 1 and the other is a 0. We use 5 volts to represent a 1. We use 0 volts to represent the binary number 0. And then it says explain how voltage levels are used to represent those bits. Well, that's what I just mentioned. I got ahead of myself. 5 volts represents or stands for binary 1. 0 volts, binary 0. Explain how voltage levels are interpreted by a digital circuit. Well, that goes back to that second handout. You can look at figure 1-2. That's when we were doing the sampling. It looks at the analog signal. It samples it at a certain point. It equates that sample. There's like a 1-to-1 relationship between the sample and a digital code assigned by the system, and then it stores that digital code. So basically, we take analog information and we store it as a number or code. Explain serial and parallel data transfer, state the advantage and disadvantage of each. Well, we just kind of went through that, didn't we? Serial data transfer means you're sending out data or information 1 bit at a time. Parallel, you send it out in groups. Advantage of serial is it's simple. Disadvantage is it's slow. Advantage of parallel is it's fast. Disadvantage is it's complicated, takes a lot to control it, and it's expensive compared to serial. It's a trade-off. And then it says explain how a basic shift register works and know the different types of shift registers available. Let me just go back to the camera. I went through that kind of quickly. So the way to look at that, just think of a register as a box. It's a box with cells in it, and those cells can store ones and zeros. And I showed you this before. It's really, really simple to think about. Let's just say we have a 4-bit register, so I got 4 cells. And all we're talking about here is how to get data into it and out of it, and that's how you name the register. So if I have 4 cells and I have 1 line in and 1 line out, this is a serial to serial shift register. Serial in, serial out. I might shift the bits in on 1 line, but I might have 4 lines connected to each cell. So I can shift the bits in 1 at a time, but they can all come out at once. So this would be serial in, parallel out. Or maybe I have 8 lines coming in and 8 lines going out. So I got a line going into each cell and a line coming out of each cell. And so if I had a binary number, 1100, when that clock clicks during that first bit time, all these load up at once. So in 1 bit time, I get all those bits loaded. And then 1 bit time, if I want to read what's in there, the next click of the clock, I can read all those bits right away. I can do everything in parallel. So parallel in, parallel out. I showed you a serial in, serial out, serial in, parallel out, parallel in, parallel out. Just look at from the way it's structured, you can kind of name the register and the way the data flows. So that shouldn't be too much of a problem. So I think that pretty much on that objective sheet, let me just go back to it real fast. Yeah, I think that pretty much covers everything. And I think we talked about everything over here. We didn't really talk about the gates, so don't worry too much about that, about the gate. We'll talk about that. All the gate is You know the and, or, not logic. Well, we actually have integrated circuits. We don't use physical switches or even relay contacts. We have actual integrated circuits with the circuitry already built in it, and they refer to that as a gate. But you don't have to concern yourself with that now. That's coming up later. So anybody have any questions over the week 1 objective sheet? Any questions or comments?
What's an inverter?
An inverter, oh, that's a good question. An inverter is just another name for the not function. So, you know, when we represent the not, we use this. We use a normally, and actually I do it the other way. We use a normally closed button. So when I talked about those truth tables and the and, or, not logic, we use that to represent our not logic. What will happen is we'll have a gate to represent, instead of showing switches in series, now I'm kind of jumping ahead, but I'll just show you real quick. You know, and logic works like this. So if I have a 2 input and, I got 2 switches. Well, we have a symbol that we use. You don't want to have to draw relay contacts or switches in series all the time to represent and. So what they have is they have a gate symbol that you use to represent and logic, and it looks like this. And so each switch would be an input over here, and then whatever you're controlling over here, that's your output. So that's a gate. Well, or if I take the same 2 switches and I put them in parallel like this, and remember they have truth tables associated with them, so you know how and logic behaves. You know how or logic behaves. So I got switch A, and well, instead of drawing this circuit, they have a symbol to represent or logic. If I have a 2 input or, I'm going to show the inputs on the left, A and B, and whatever it is I'm controlling over here on the right, we just call it X. So this is the symbol for and logic. This is schematic symbol for or. Well, for not logic, they call that an inverter. An inverter. And the way they show this, the gate symbol looks like this. The symbol it's like a diamond or a triangle, and it has a little bubble on it. And this is the only one of the logical functions that has 1 input. So 1 input. So this represents not logic, not. But they call it the gate, and gate, or gate. The not logic, they call that an inverter. And the reason they call it an inverter is whatever bit you put over here, like this one, you know how it behaves. If I have a 1 here and a 1 here, then this is true. If I have and logic, 1 0 on the input of an and, that means that the outputs false. You know that from the truth table. But the inverter is interesting because it flips the bit. If I put a 1 here, and then on the output of this, I get a 0. I put a 0 into the inverter, on the output I get a 1. So that's when I always use that normally closed push button for not logic, and I said, well, it's kind of hard to explain with the switch. When I get to the gate notation, it'll make a lot of sense. Now, guys, I don't know, there's a lot here. You know, we take a lot of things for granted. Pretty much if you take out your cell phone, and you can use your cell phone for a calculator, and you say you type in 2 + 2. It's taking those numbers, those decimal numbers, converting them to binary, machine language, and then using and or not logic to do whatever mathematical function you want it to do. And we'll get into the details of it. You can see how it does it. But it's pretty amazing the way this stuff works. So, you know, you're getting some stuff here that if you sit back and think about it, you'll understand a lot of devices on the level that you didn't understand before. So I'm getting too much off track. Anybody else have a question? I want to move on, if you don't, to this week's material. I want to get through this first PowerPoint. So anything else on this sheet? Why don't you just look at it, guys, and then if you have other questions, ask me about it on Wednesday. And I'll probably do the quiz. I don't think I'm going to do the Friday thing. I think I like the thing where I set it to show on Friday and give you the whole weekend to do it. That way you can do it whenever you want. Because before I had on Friday, we start class, and the first 10 minutes of the class, they do the quiz. I think I like it better. You're more relaxed at home. You know, you can kick back and you take the quiz. So I think I'll keep it over the weekend. So from now, between now and Friday, look over this. If you have any questions, please ask me. I'll be happy to go back over it. Now, let me show you something before I get into the material. I don't know if you can make this smaller or not. Let me see. I can, yeah. I can use my magnifier to bring that out. But all this is if you were meeting me face to face, when we met face to face for this class, I would have to get a 3-ring binder, and I would come in and I would pass out all these PowerPoints. The next few lectures are going to all be on PowerPoints. Just no other way to teach that material. I recommend you print out the PowerPoints like this, where you have 3 slides to a page. I think they call this note pages. That way, you know, when I'm talking about something, you know, you can just take notes over here and put that in your 3-ring binder if you got a 3-ring binder. Because often what I'll say is, this is important for the exam, or this is important for the quiz, and you can just write it next to that slide and write whatever it is we're talking about. This is a really, really good way to study. So as you go through, I would not keep the PowerPoints on Canvas and go back and look at them. If you have a printer, I would actually print them out, put them in your 3-ring binder, and make notes on them as we go along. I mean, I hate teaching from PowerPoint, but there's really no other way to get this material across. So I recommend doing that. And now let's talk about PLCs. So normally what I do, what I've done in the past is I have a PLC, and when we were face to face, I would bring it in and I would take it apart in front of the class. We would examine the parts and talk about it. That way, when we go through these other PowerPoints, you kind of have a reference. You have a physical reference to what I'm talking about. But I think the last year before COVID, I stopped bringing it in because, to be honest with you, the thing is kind of heavy. And I had my nephew with me. One day he came up to the school with me just to carry the PLC over to the class. And then he met me back after class to carry it back because I'm getting too old to carry it. So well, now I'm just showing this picture of the PLC. So here is a kind of general PLC. I want you to look at this closely. And I want to talk about some of the pieces of this. And you'll be able to relate this to, as we go through the PowerPoint when I talk about it, think back to this diagram. So the first thing to notice is that PLCs, now there's different kind of PLCs. I'm talking about they have small PLCs about the size of a pack of cigarettes. They might have 4 or 8 outputs, maybe 8 outputs if you're lucky. And they're about the size, maybe a little bit bigger than a pack of cigarettes. I'm not talking about those. Most other PLCs, larger ones, are modular. They're modular. And what do I mean by modular? Well, they're actually separate pieces. So you have this piece right here, which they're calling the power supply. Well, that's a separate unit. You can actually separate it from the rest of the system here. And then you have this communication module. Over here you have the I/O system, that stands for input output. And then some of these are input modules and some of these are output modules. But again, you can actually disconnect this input module, you can take it out, and then there's a slot right there. You can actually snap another or plug another PLC module into that. So most PLCs are modular like this, so you can easily change out the pieces. Let's look at the types of modules. Well, every PLC will have a power supply. That's a piece of a power supply. Every PLC will have this controller. Now, on some PLCs, depending on which one it is, they'll call it the controller. Sometimes you'll see it referred to as the CPU. The CPU stands for Central Processing Unit, and that's the part that houses the microprocessor. So every PLC will have a CPU. So the I/O system consists of input modules and output modules. The input modules are where you wire your input switches or sensors. The output module, that's where you wire whatever it is you're controlling, or the relays to control whatever you are controlling. not every PLC has a communication module. So this one does, but not every one. But every one will have a power supply, CPU, input module, output module. So those are the basic systems or subsystems of a PLC. Now, the PowerPoint I want to talk about today is it just gives you an overview, kind of an overview of the PLC. And so it's kind of a, what can we do with this thing and what advantage does this have over hardwire relay control, logic control systems. And so we'll just kind of take an overview and then we'll get into some of the specifics in the next class. So, definition of a PLC, with no one say computer on steroids, a PLC is a solid state device designed to perform logic functions previously accomplished by electromechanical relays. So a couple terms that's important here is the term solid state. It's a solid state device. It's not a discrete device. It's a solid state. And just the best way to understand that is there's no moving parts. You can have a switch, a physical mechanical switch where you can move a lever to turn something off or on, but you can also have a solid state switch. It's called a transistor. And a transistor is a switch built out of a solid crystal, and there's no moving parts, but yet you can turn devices off and on with it. So the most basic meaning of the term solid state is an electrical term or a physics term, which means is there's no moving parts. It's derived from a single solid crystal, and the crystal is usually silicon. So solid state, no moving parts. Electromechanical relays, well, we studied those in detail. You looked at the relay that I drew on the board on the day one of the class, and when you did quiz one, he took you in the relays and how they work. There's two kinds of relays. There are relays we use for logic relays, and then there are relays we use for control relays. So Jeremy in the video, when you guys watched that for the quiz, he had in there control relays, and he had a contactor, which is just a heavy-duty control relay. And you use that because you can use a small amount of power to switch on and off a large amount of power. So that's a little different than logic relays. Logic relays are smaller relays, and we just connect the contacts in series or parallel, depending if we want and or logic. So you should be familiar with that. Well, what kind of things can a PLC do? Now, they can do other things, but the main task that pretty much any PLC can do, relay switching. It can switch devices on and off just like a relay, turn things on and off. It can count. It can calculate. By calculate, it can add, subtract, divide, multiply. Most PLCs will have some kind of math function. It can compare. And then it can, it says analog signal processing. Analog signal processing. What the heck does that mean? Well, depending on the kind of PLC you have, if you have a input module that's analog, that means you're taking in analog information and you're feeding that into the PLC. But to do that, remember, all digital devices only understand machine language. So you can't inject the audio, or you can't inject the analog signal directly into the digital device. You first have to change it over to something that can understand. You got to do an analog to digital conversion. And in doing that, sometimes signals might have noise on them, or they might pick up noise, so you have to clean the signal up. So this idea of analog, the term processing means a whole lot. Basically, for you, you can take an analog signal and change it to digital. We'll suffice it to say that. What about advantages over relay control? Well, you can probably think of a few yourself, but here's some of the main ones. Relays have to be hardwired. So remember the example I gave on the first day of class, where back in the old days, if you were Ford or General Motors or Chrysler, and you're making cars, and back in those days, the model year changed every 2 or 3 years. And so you have these machines and logic circuits based on relays, and maybe you have a circuit to sense the presence of a automobile chassis, and to count the number of bolts that's been put in by some kind of robot arm or whatever. Well, when the car model year changed and the design of the bumper changes, the logic in the circuit to control changes, and you have to go in and actually rewire the relay contacts. You have to have an electrician come in and rewire those contacts, the logic portion of it and the control portion of it. Well, as you might imagine, if you're General Motors or Ford, that's a wiring nightmare. So one advantage that a PLC has over relay hardwired circuits is when you have a control system, probably 85 to 90% of the wires is just for the logic part of it. The control part of it, there's not that many wires to it. And so if you can eliminate, basically take away the logic part of it, you're left with relatively simple control circuits. So all of that, what would have been logic relays, contacts wired in series and parallel and combinations of those, you replace that in software. You do all your, and I'm doing air quotes right now, you can't see me, you do all your wiring in software. If you make a mistake, you don't have to rewire anything. You just delete it and drag and drop another command and you're good to go. And that's kind of what this class is about, to get you to understand how to write those commands to control some kind of industrial system or some kind of process that you want to automate. PLCs are smaller in size. You can, if you had a control panel with relays, it will take, on average, they might be the size of a refrigerator. They're big panels with hundreds of relays on them wired up. You can have a PLC the size of a pack of cigarettes. Typical PLC is about the size of an average tower that you might have on your PC. Solid state, we said, think about that as meaning no moving parts. If there's nothing moving, there's nothing to wear out. Typically, when you can replace something mechanical with something electrical, if you have a mechanical switch that moves all the time, eventually, because the stresses on the switch, is going to wear out. If I have a transistor and that's acting as a switch, I can turn that off and on as many times as I want and there's nothing to wear out. So solid state devices don't wear out. Now, that doesn't mean they're perfect, because what kills electrical devices is heat. Over time, heat can affect these devices and then they break down. So while it's a big advantage to have a solid state device, it doesn't mean that they're perfect. Solid state devices, by their very nature, they consume much less power than actual hardware. If you think about it, a relay coil, although it pulls, since the coil circuit is a high resistance circuit, as we talked about in week 1, that means the current or power draw is going to be really small. Compared to a solid state device, a relays probably pull on the order of milliamps. I'm talking a small control relay, milliamps, whereas the solid state devices can pull microamps. So they're much more efficient. PLCs you can expand them really easy. Why? Because they're modular. You can unplug an analog module and plug in a discrete digital module if you want. You can just unplug one part and plug something else in. So you can expand them. And then security, since a PLC is a computer, any kind of way you can secure a computer, you can secure a PLC exactly the same way. So how can we secure a computer? Well, you can put a password on it. You can put a password on the PLC. You can pretty much anything you can do. You can network it. You can use any kind of way you can think of securing your cell phone, a PC, a laptop. Any of those ways you use to do that, you can do the same thing with the PLC, because a PLC, a cell phone, they're all the same device. They're just fancy microprocessors. So many advantages over hardwire control systems. Now, you want to mark this down, or at least write yourself a note, because I'll ask you at some point what this means. A PLC is an event-driven device. The PLC is an event-driven device, And to understand how PLC works, you really want to understand this statement. Most of the time when you have a computer, a program, you write the code, and the program is sequential. And when you start the program, you run through certain steps. PLCs don't work like that. PLCs work like this. They sit there and they don't do anything. They just monitor inputs. And when a signal comes in from an input, and the input could be a switch, it could be a sensor, and we'll talk about the difference between switches and sensors. But you got some kind of signal that comes into the PLC. If it's a digital signal, it can use that signal right away. If it's an analog signal, it's got to process it. It's got to change it from analog to digital. But at some point, it's monitoring the inputs, and then it's going to look at the program that you wrote to say, hey, what do I do with these inputs? You're going to use and or logic to determine what to do if you have the conditions and what to do if you have that set of conditions. That's the program that you write. And so when you write the program, depending on the outcome of the program, it's going to adjust the outputs accordingly. So it's going to sit there, and if there's no event that happens, a switch doesn't open or close, or sensor doesn't send out a signal, it's just going to sit there. Event-driven means something has to happen in the factory, we call it the field. Something has to happen outside the PLC, and then the PLC is going to respond to that event. So the term event-driven is important. The parts of a PLC. You just probably want to remember these. Same as any old computer, any device, any digital device. You got a CPU, central processing unit. There's going to be a way to get data into and out of the computer or PLC. My lights went out, so I'm walking. There we go. I'm trying to beat the clock, and I'm trying to keep my lights on at the same time. So there's going to be an I/O section. Your cell phone has an I/O section, power supply, and some kind of way to program it. So all digital devices, all PLC, all computers have these parts. And here's if you like to remember pictures, here's a picture. This actually comes up in a lot of PowerPoints. So these are the pieces that you'll have. So you got to have a way of getting data into the CPU. That's going to be the input module. All your switches connect to this. You got to have a place to put those zeros and ones. Once you get them into the PLC, they're going to be stored in memory. You got to have a way to process it. So your CPU does all the processing, all the math, has the clock and everything built in the CPU. You got a power supply, of course, you got to power it. And then whatever you're controlling is going to connect over here to the output module. This part right here, you got to have a way of logically telling the CPU what you want to do with those inputs using logic. Now, here's the thing, one difference between a PLC and a PC. With a PC, you keep the keyboard there all the time. But once you put the program in the PLC, you don't need the keyboard anymore. So often, I know some of you on your co-ops, you're already familiar with these devices, PLCs, but it's common to walk in and the PLC just looks like a module on the wall with no keyboard connected. You don't need the keyboard if you're using the program. Only time you need the keyboard is when you're going to edit the program. You got to make some kind of a change. Guys, it's 2 o'clock now, and I know you guys got to take off, but I'm almost done with this PowerPoint. So if you got to take off for another class, go ahead. Just make sure you go back when I post this to YouTube and you watch the tail end of this. But I'm right here, so I'm going to finish this, and then I'll put it on YouTube, and you guys can watch the end of this. Here's some common input devices and output devices. I'm not going to say too much about this slide because as we go through the course, you'll become familiar with these input devices and output devices. So you can look at these. Now, this slide is really important. So mark this slide, or at least write yourself a note if you don't have a printout. You need to know the difference between a field device and a real field device or real world device and a virtual device. So a field device is hardware, anything you can hold in your hand. So a relay is a field device. A light bulb is a field device. A single pole, single throw switch is a field. Any kind of thing you can actually touch is what we mean by a field device or a real world device. A virtual device only exists in memory. Virtual devices, basically they're software. They only exist in memory. The thing is, we can have PLCs mimic real world devices, which turns out to be really, really, really nice. Examples of devices that can be mimicked by a PLC memory. Relays. We can have a relay in the memory of a PLC. Timers. The old PLCs had mechanical timers. Well, we have software timers and counters. Now, the reason that's so nice is in the old days, let's say you needed 10 counters. You have to go out and buy 10 physical counters. Here, you can have thousands of counters because all it is a space in memory. So there's so many advantages, and I don't have time to go into those, but you do want to understand the difference between a real-world device and a virtual device. Virtual devices only exist in memory. And here are there are others, but here are the main three types of real-world devices that can be mimicked by the PLC as virtual devices. Relays, timers, counters, which with relays being number one. Counters and timers are probably on the same level. And then, how does the PLC system work? So take a look at this. Just take a second and read this, because this will make clear what I've been trying to tell you about as far as how the whole system kind of comes together. So take a look at this. So I tried to, my artwork isn't the best, but what you have here is you have this tank or vat or whatever they call it. You have a motor. You have a field valve. Now you got a couple sensors and switches in here. You got a pressure sensor right here. You got a pressure sensor. And then you have a temperature switch. Each of these are inputs. So there's two inputs, but actually there's three, because you also have a manual start-stop button. So you have three inputs. And the output, I don't know if we're controlling the field valve or the motor. Let's see. The problem statement says the mixer is used to automatically stir the liquid when, now you gotta be careful. Anytime you see the English word and, or not, that's when you start thinking logic. So the mixer is used to stir the liquid when temperature and pressure reach preset values. It says also the mixer can be controlled directly by the push button switch, the manual switch. So logically, what are we saying? Well, what we're saying is the mixer is used to automatically stir the liquid when temperature and pressure, that's an AND circuit, or the push button. So we got an AND logic or logic. So if I want to wire that with mechanical switches, how would I do that? Now notice here, they give us some information here which turns out to be important when you're working with PLCs. They tell you how the contacts work, normally open and normally closed. But if I want to wire that up, the control circuit might look like this. So this is a very simple logic. The way you read these is you start with on the left over here, and think of current flow from left to right. It's not really current, it's really logic, but for now current. So if you look at the way this works, the way it's wired up, if the pressure switch is closed and the temperature switch is closed, there's a path for current through the motor comes on. Or, as we said, those two conditions have to be met, or if the manual push button is pushed, then current has a path. So here's my AND OR circuit. Here's the AND part, and that's the OR part. So we combine the two logic, and then we get the logic as needed as the problem statement says. Now what you would do though, if you didn't want to do this, if you wanted to do this with a PLC, you didn't want to use relay contacts or switches to hardwire this, you go buy a PLC, and what you would do is take those switches And you would just connect those to this is the input module right here. This is the module that I showed you earlier on the picture of the PLC. This is the input module. And that input module has terminal screws on it that you can connect wires to. So what you're going to do is connect all those switches directly to the input module. Notice we're not concerned about logic at all. We're doing is this line right here, line 1, is power. This is the power line. Basically, we're just connecting our switches from the power line over to these screw terminals. Now notice each screw terminal has an address. Pressure switch 001, temperature switch 002, manual switch 003. Once you make those connections, look at how we do the logic. You turn your PLC on, and now you're looking at the screen, and this is the program you're going to write. This is not an electrical circuit. This is software. These are instructions to represent the switches. And the way we connect the temperature switch and the pressure switch and the manual switch to these instructions is, remember what I said before, those terminal screws each had an address. And so at 001, if that was a temperature switch, we know what it's connected to. Pressure switch might have been 002. So now that we have those addresses, basically these addresses map your instructions, your logic instructions, to the physical switches. So this says take whatever's connected to terminal 001, address 001, and put it in series with whatever's connected to 002. Well, that's AND logic. So these two commands have to be true. If these two are true, then whatever's connected to the output, now we're on the output, the output module with this address 009 is going to turn that thing on. Or if whatever's address has address 003, which is manual push button, if that's true, it's going to directly turn whatever's connected to this output on. The point is, it's all done in software, so if you make a mistake, you don't have to go in and rewire anything. You go in, you delete this, you drag and drop a new command, or you can change your logic. It's all done right there on your computer screen. It's quick and it's easy. So guys, I'm out of time now. These other slides, it's good for you to read. I mean, this one, I'll have you read that on your own, these cycles. And then this was not a big deal. There's two types of PLC software. There's programming tools, which is what we'll work on. How do I get my program inside the PLC to tell it how to handle the logic that I want? And then there's monitoring software. You can have a system set up and have actual virtual layout of whatever it is you're controlling, just so you can watch what's going on in the system or in the process. So sorry I went over. That's all for today, and I'll be happy to stick around if you have questions. But other than that, guys, have a great rest of the day, and I'll talk to you on Wednesday. Anybody have any questions? I'll stick around. Just let me know.
Hey, Professor. I just have a question about homework 1.
Okay.
So I finished it like last week, but I just forgot to turn it in until this morning, and I wasn't able to like submit it, but I submitted a note where I attached the file to it, and I was just hoping that you got that. I don't know.
Where did you submit it to?
So I opened the assignment, and then it said that I could submit a note. So I submitted the note, and then that note said that I could attach files to it. So I attached the homework file, and then I attached a screenshot like showing that the file hadn't been edited since like last Thursday.
Okay. Hey, do me a favor. Who's talking right now? Who is that?
This is Aaron.
Hey, Aaron, do me a favor. Go ahead and email that to me. I mean, you're probably okay. I'll probably see it when I get to Canvas, but it seems complicated, whatever you said. So just to make sure I get it, go ahead and send me that to the email that's on the syllabus, ronsingleton@hotmail.com. It's on the syllabus. Send that to me by email. Once you've sent that, whenever it is, just send me a text and say, hey, I sent you the assignment. And then in the next day or two, I say by next class, if I haven't went in and graded it, then just remind me when I get on camera that, hey, you didn't grade my assignment yet. Okay?
Okay. All right. Thanks a lot.
All right. Thank you. Anybody else have a question? Okay, well, we're going to end here, guys. I will see you